Check 1 2 1 2 3 4 5. Check 1 2 1 2 3 4 5 6 7 8. turn it off. When you want to speak, turn it on. Speak.
I think if you mute it, I'll give you a cue.
How?
I will be here. The stage is unmuted. Just go on. It's all yours.
And it all works.
The slides just come up automatically?
The slide is up.
Oh, it's nice.
And you know how to change it. Why don't you stay there and I'm just going to the side.
Okay, let's stay here.
If you need to scroll there.
I don't need to scroll back, as long as the slides are up, yeah. Good.
Okay, everybody, can I have your attention, please? Thank you very much. So, we were wondering what to do about a little bit of entertainment, and we've come up with a plan. So, today, there's going to be two speakers, Doug Gurr and Benjamin Pierce. Now, Doug Gurr was a PhD student of Gordon Plotkin's. At some point a bit later, he became head of Amazon UK. He's now director of the Natural History Museum. And Doug and Benjamin will talk about climate change. So thank you, Doug, so much for coming and talking to us.
Thank you, Philippa. Great to be here. Sound okay? Vision okay? All right, slides up, slides not up? Not yet. Slides up, great. Brilliant. Well, listen, thank you very much indeed for letting me come and, I think the phrase was entertain you for a few minutes. I'll do my best. If it's a disaster, let me know. Anyway, as Philippa mentioned, my current day job is Director of the Natural History Museum. And you probably know us. Anybody visited recently? Excellent. You probably know us as a large visitor attraction with dinosaurs in South Ken. We're also a research institute. Have about 350 full-time academics, currently 172 PhD students, and very much focused on these questions of climate and biodiversity. So if I may, I thought I'll give you a quick history lesson, because we do Planet Earth, life on planet Earth. Talk a little bit about where we are, what's good, what's bad, and particularly talk a little bit about what the role of scientists like yourselves is going to be. Sound okay? Great, brilliant. So let me take you back. The Earth on which you currently stand was created about 4.5 billion years ago, 4,500 million years ago. And life emerged after about 1 billion years. So life's been knocking around for about 3.5 billion years. And for the first 3 billion years, that's 3,000 million years, just in the oceans. So about 500 million years ago, life finally emerges onto land. And I've got a little slide for you here, which I nicked from my friends at the Smithsonian, which is quite interesting. This is the average temperature of the Earth over the last 500 million years. And the bits in red, which as you can see is about 70% of the last 500 million years, those are periods in which it would have been too warm to have any ice at the polar ice caps. Bits in blue are those periods when you actually do have ice at the polar ice caps. So as you can see, a couple of things to sort of point out for you. One is it varies, obviously. And we have pretty conclusive good data to say that over any period of time, the actual regulator of the Earth's temperature is atmospheric CO2. And you have processes that generate it, which are primarily volcanic eruptions, things like this. They spit CO2 out and the destruction of fossil fuels. And you have processes that sequester it, which is weathering of rocks and things like that, and biological processes. Life on the whole captures CO2. So you have these fluctuations. And just a couple of other points, as you look through this, you'll see there have been periods in which you have quite dramatic shifts in quite short periods of time. And there have been 5 of these. And on each occasion, just 5 in the last 500 million years, you've had a sufficiently radical and rapid change in the environmental condition that it's taken out almost all life that existed. So we call these mass extinction events. Just 5. Haven't had one for 66 million years when the asteroid strike took out the last of the dinosaurs, non-avian dinosaurs. So very rare. One about every 100 million years, and you lose between 70 and 95% of all extant species. So rare, infrequent. And just bringing you slightly up to date, if you look at the last bit on that slide, you'll see that actually, for about the last 6 million years, it's been unusually cold and rather benign conditions for Homo sapiens. So we've just happened to lucked out in quite a generous period. And that teeny little spike you see at the end is the bit you'll all be familiar with from the ice core work and so on in terms of the rapid rise. Or as we like to say, mean reversion. Okay, just so we're clear. So, mass extinction's pretty rare. And we've spent quite a bit of time studying a series of events that happened about 200 million years ago. This is a particularly interesting series of events because they're the ones that are most similar to the conditions we're seeing today. And if you look here, this is, if you want to go and look at this is not far from here, Staithes off the coast of West Yorkshire near Whitby, which is actually the best place in the world to study these particular events because the tectonic plate tilt means that if you walk a 2-mile stretch of coastline, then at eye level you can walk through 100 million years. And that 100 million years perfectly spans this mass extinction event. So you spend a lot of time studying it. And it's a very interesting series of events. So go back 200 million years, Europe is a shallow archipelago quite close to the equator. And you had over a couple of centuries an enormous amount of tectonic plate movement in the southern hemisphere, massive volcanic eruptions, big increase in atmospheric CO2. Guess what? CO2 goes up, and 2 things happen. First of all, the planet warms, and it did, somewhere between 3.5 and 6 degrees. So not orders of magnitude away from the kind of numbers we're looking at now, albeit the CO2 level was much higher, 1,500 ppm versus the 450 we're seeing now. So the planet warms. But the other bit is some of that CO2 dissolves in the oceans. Clear? And when CO2 dissolves in the oceans, it forms a very weak acid, very, very weak, but over a period of time, it gradually increases the ocean acidification. And when you study this, you can see really clear in the areas of LOX. You look at the nanofossils, the microplanktons, the forams, all of this sort of stuff, the pollens, and you see a period where everything's fine, everything's fine, everything's fine, everything's fine, bang, gone. Gets a little bit too acidic. Why does that matter? It matters because right at the bottom of the food chain, you have planktons and forams that have calcium carbonate shells. It gets quite hard to form a calcium carbonate shell as the oceans get more acidic. And when that collapses, the marine ecosystem collapses, the terrestrial follows. And in that particular series of events, we lost 95% of all extant species. You know, that's when the ammonites went, that's when a whole lot of other things went, and it took about 6 million years to recover. So, bad news. Fast forward to today. So if you look at the little chart on your right, you'll be familiar with this. The purple line is atmospheric CO2. The dark blue line is the partial pressure of CO2 in the oceans. And the pale blue line is the increase in ocean acidification just over the last sort of 30-odd years we've been measuring it properly. So the acidification is going up. So what? If you can see on the left, these are CT scans of forams, these are sort of, right at the bottom of the food chain, little planktons. And you've got on the left one, you've got samples that were collected on the Challenger expedition in 1872. So the first big global expedition things. We still have those samples, and we've CT scanned them, you can see. And on the right, you've got stuff that was pulled out of the oceans about 2 years ago. And the scary bit is that we've seen a 76% reduction in shell thickness in 150 years. 76%. Again, this is not a prediction, massive uncertainty, huge error bars, but if you go forward and fast forward and simulate likely seawater conditions by the end of this century, which is only 30-odd years, 70-odd years ago from now, there's an enormous number of species that can't survive. So it's quite urgent. New news? Everybody knows this? Awesome, very good. So, how are we going to fix it? So the good news is this is a very fixable problem. Very fixable problem. What you have to do, first of all, is stabilize and hopefully reduce the level of atmospheric CO2. If you get that right, it's fine. And actually, from a computer science point of view, that's quite a boring, easy problem to solve. Yeah? We know exactly how to do it. It's not that hard. Solving climate is you just have to get atmospheric CO2 down. Because it's a fungible gas, it honestly doesn't matter where you do it or how you do it. You can do it through biological solutions, you can do it through carbon capture and storage, you can do it through reducing fossil fuel emissions, and, it's in condition. It's no good stabilizing the Earth's temperature if you've also poisoned all the oceans and cut down all the rainforests. You're still stuffed. So as well as worrying about the climate crisis, you have to think about biodiversity. And my final few points here before I close down and let Ben come in is that biodiversity is much more interesting from a computing point of view because climate doesn't matter where you do it, how you do it. Biodiversity is very different. Biodiversity is very different because it's much more heterogeneous. There are parts of the world where it's really important, parts of the world where it really doesn't matter. And so if you're a follower of the regulatory framework, the Montreal Kunming Agreement, back end of 2022, was really important because that said 30 by 30. Can we protect 30% of the Earth's most important terrestrial and 30% of the Earth's most important marine systems? And the good news is if you can do that, that's enough because those contain the vast numbers. So here is the most important 30%. Optimized at country level, because for policy you tend to work at country level, marine and terrestrial. And if you can protect this area and restore it, you're actually in a pretty good place. So this is really a fixable problem, Stabilize, get the atmospheric CO2 down and protect this. And this is where we start to need your help because you need a ton of data. Here's the UK. And if you look at these are the areas that really, really matter. And the UK is a great example of actually a seriously degraded ecosystem. We are currently the 17th worst in the world in terms of intactness of the critical national assets. Really bad news, but very fixable. And solving it has to be solved at a really micro detail level. The other problem I'll throw out to you, and then I'll throw out a couple of things where I think you guys can really help. These are the 5 parts of the world that have degraded the most over the last 20 years: Bhutan, Cambodia, Niger, Solomon Islands, Bahrain. Not necessarily places you'd think about, but the ones where it's really collapsing and collapsing fast. In many cases, these are the most critical areas. And we ain't going to solve these problems unless we can get a level of granularity and precision about exactly what you do, where you do it, and how you do it. And the bit where I think there's an extraordinary opportunity to lean in is solving superhuman scale problems. Let me give you one example, and then I'll close down. We've been studying biodiversity for about 270 years, seriously, since Linnaeus. On the most generous estimate, we're about 20% of the way through the job. So we can either wait 1,000 years, or somebody in this room can get serious about helping us to turn humans into superhumans using the skills you have. So if you're up for that, come and have a chat. That would be awesome. Thank you very much indeed.
Maybe a little bit jumping.
excuse me, guys. Those people enjoying themselves over there by the bar, can you be a tiny bit quieter? Just a little bit. Thank you.
All right. All right. Thanks, Doug. And this is going to be short, I promise. I just wanted to add a more, let's say, SIGPlan-centric or PL-centric point of view to what Doug already said. So lots of people in this room are already doing things about climate change. Others may be looking for ways to help or more ways to help. And so I'd like to offer just a few brief thoughts about that. We each have many identities. We each participate in many interlocking organizations of various sizes. There are opportunities for climate action at every level. The ends of this spectrum are the easiest ones to talk about, so let me do that briefly. So first, at the level of individual action. There are lots and lots of things to do. We should absolutely be doing these things, but I'm not going to spend time talking about them, both because they are pretty well known and because it's also pretty well understood that making these sorts of changes is absolutely not going to solve the global problem. So let's move on. Moving to the other end of the scale, what about the biggest stage for action? What can I do as a member of whatever country I live in? And the answer is basically one thing, and I hope you're doing it. That's obvious, let's move on. Things get more interesting at more intermediate scales. So first, what can I do in my specific capacity as a PL researcher? To be honest, I have not yet found a lot of opportunities. That's not because they're not there necessarily, but I've been looking and I haven't found them yet. But that may be starting to change. On Saturday, right here in this building, there will be the first instance of the ACM workshop on programming for the planet, organized by Dominic and Anil. I'm very excited to see what people are going to have to say. I hope you will come as well if you're in town and interested. So maybe I'll find something I can do at the workshop on Saturday as a PL person. That would be nice. Something that would use all my skill and background and that would be fun in the way that research in PL is fun, and maybe even I would get paid for doing. That would be nice. It would be great, in fact, but does it have to be that way? No, of course it does not have to be that way. Throughout history, most big social change has come about through the actions of people who were not being paid to do it and whose main job it was not. So with that in mind, let's broaden the scope a little bit and ask, okay, maybe not as PL researchers, but what about as computer scientists? What can we do? And now there are a lot more options. So to begin with, there are things we can think about doing as computer scientists, but of a more, let's say, political nature, like figuring out how to run conferences with a lower carbon footprint. You may know that I and others in this community have worked pretty hard on this in the past. There is undoubtedly more to be done in this domain, but there are technical things too. So let me move on to those because I think they actually may have bigger potential impact. Here are just a few, and there are many others. If you're interested in machine learning, there are many connections between machine learning connections and potential applications between machine learning and climate change. There is a wonderful survey article in Computing Surveys by David Rolnick and a bunch of other people about kind of enumerating a vast number of places where there might be connections to be made. There are, you could think about improving distributed systems, the way distributed systems work, so as to better support climate science. And this is something that our friends Dominic and Anil are very much involved in with their colleagues in Cambridge. There are efforts going on, of course, in many other places. There is virtual conferencing. I was heavily involved in that for a couple of years, as you may know, with the Midspace platform. I think in terms of technology, we're not quite there yet, but I think we will get there, and this will be very interesting in the future. And finally, there's trying to address, or finally on this slide, there's trying to address the carbon footprint of all of the computing that we do at a hardware level, both the embodied carbon that that goes into things that we manufacture, and the operational carbon as we run things. And with fingers crossed, there may be a new NSF expedition coming out, led by people at Penn and Harvard. So just some ideas. There are many other ideas to look for across computer science. Another place to look for potential impact, and I want to close with this because it's one that has been very successful for me personally, is to look for places to make a difference in your organization, your university, company, whatever. And this is probably an easy place to get involved because these organizations are often reasonably small. You probably know the people that might know what's going on, and probably there is plenty going on and plenty more hands needed. So my experience at Penn has been exactly this, that there was a lot happening, but people were eager for more help. My personal area has been working some more on carbon offsetting because I already knew something about that, but there are groups at Penn and every university pretty much working on operations and buildings, working on curriculum, et cetera, et cetera, et cetera, working on community outreach, lots of opportunities. So this is the easy way. So I hope this has given you some ideas. If you'd like to chat, I will be here the rest of the week. For now, please enjoy. Thank you.
Can I just thank so much to Doug and to Benjamin? And I happen to know that there's some people here that are really keen on climate change and getting involved. If you want to, come over here and come and get a discussion going. Okay, and don't forget, it really helps to get your drinks in before 2 minutes before 7:15. Remember. Thank you.